In this video, I'm going to talk about weak base, Kb, and also pKb. Now, one thing about weak base that I want you guys to understand is that a base generally is a substance which, when dissolved in water, it produces hydroxide ion, right? That's according to the definition of what? Of Arrhenius, right? And as far as Bronsted is concerned, Bronsted and Lowry define a base as a proton acceptor. But one thing I want you guys to understand is that the strength of a base is the ability for that base to produce this hydroxide ion when dissolved, when react with what? With acid. That's what I want you to understand. And second thing is that it's not actually all base that actually have this hydroxide ion, right? So in that scenario, that is that whenever we want to talk about base, we talk about them with respect to their ability to accept a proton. So strong base, they actually have the ability to accept a proton rapidly compared to what to be the big base, right? And in order for us to calculate the strength of a base, or to determine the strength of a base, we make use of Kb, right? Kb simply means the base dissociation constant, base dissociation constant. And suppose we have an unknown weak base, we have BOH that undergo dissociation to give us what? B plus what? OH minus. So we apply the before and after reaction, or before and after mechanism. We are going to have before the reaction, right? Before the reaction, we actually have C amount of this, and we have 0 amount of this that is produced before the reaction. Then after the reaction, right, we are going to have X amount of this that is produced, X amount of this that is produced. Then we are going to have what? C minus X amount of it that is produced. Now in that scenario, we are going to write out the Kb for this reaction. Kb is going to be equals to what? Concentration of what? Of B plus multiply that of what? Of OH minus. That's what we are going to have. Then divided by what? Concentration of what? Of BOH. Now from there, if you look at this very well, we are going to have the Kb to be equal concentration of what? Of B plus at equilibrium is going to give us what? X. Then multiply what? Concentration of what? Of OH at equilibrium is going to give us what? X, right? They are going to have divided by what? Here is going to be C minus X. Because the base is actually what? A weak base, we can actually what? Neglect what? X. And in that scenario, we're going to have the whole expression of what? Of Kb to be equal S squared, right? Divided by what? This is going to give us C. Then let's go ahead and what? And make X out of formula. We're going to have what? X squared to be equal to what? Kb, right? Multiply by what? C. So that shows that our X is going to be equal to what? Root of what? Of Kb multiply what? C. This Kb indicates acid a base dissociation constant. C is actually the concentration of the base. X is actually what? The concentration of hydroxide ion, right? So from there, what I'm going to do now is actually to go ahead and replace X with what? With concentration of hydroxide ion, right? If I do that, I'm going to have, let me just put the final expression here. I'm going to have concentration of hydroxide ion, right, to be equal. This is going to give us root of what? Of K subscript B multiply what? C. That's what I'm going to have. Now one thing I'm going to do now is to just go ahead and take negative logarithm of what? Of both sides, right? So if I choose to take negative logarithm of what? Of both sides, let's see what we're going to have, right? So from there, we're going to have OH constant of hydroxide ion to be equal. Here is going to be root of what? Of Kb multiply what? C. So taking negative logarithm of both sides, I'm going to have negative logarithm of what? Of OH. This is going to be equal. We are going to have this what? Negative logarithm of what? Of here is going to be K raised power 1 over 2 multiply what? C raised power what? 1 over 2. So if we apply logarithm identity here, as we are going to have negative logarithm of what? Of hydroxide ion concentration, right? So this is going to be equal. We're going to have this to be here is going to be this is going to be Kb, right? So here we're going to have let me just say I'm bringing down, I'm separating using what? Logarithm identity. We're going to have this to be negative logarithm of what? Of Kb all this power 1 over 2. Then we're going to have negative logarithm of what? Of C raised to power what? 1 over 2. So the final expression is going to be what? Minus log hydroxide ion is going to give us what? POH. This is going to be equal. I'm going to bring down 1 over 2. I'm going to have 1 over 2. Then I'm going to have this to be PKb. Then here is going to be minus 1 over 2 log of what? Of C. So this expression is also very important to calculate what? The weak acid. Let me just simply say the pH of what? Of weak acid is very, very important. This as well is also very, very important. Then from there, you guys have to take note of what? Of things that I'm going to bring out now. of this formula I'm going to write out, you have to take note of it. It's very, very important at the same time as well. So what I'm going to do now is that since we've already derived the expression for the weak base, which is POH equals to 1/2 pKb minus what? 1/2 log C. You have to understand that pKb is actually equals to what? Negative logarithm of what? Of Kb. That's what our pKb is. Then from there as well, whenever you want to relate pKb and also what? pKa together, pKb, right, plus what? pKa is actually equals to what? Is actually equals to pKw. Or you simply say 14. It's just like pH plus pOH equals to what? 14. So at the same time, if you take note of this, you have to take note of pH plus pOH at the same time is equals to what? pKw. Now, what I want you guys to understand here is that this first expression is for weak acid and weak base, while this second expression is for what? Is for strong acid and also what? Strong base. So it's very, very important for you to understand the difference between them. This actually was negative logarithm of pKb, and enough for us to get pKb and pKa. We can only determine them through the what? Through the equilibrium reaction, that is equilibrium expression. But this we can actually apply just consider what of hydrogen agent directly, because we already know that it's going to dissociate completely. So whenever acid or base dissociates completely, you can actually mix a lot of this one. But if it is partial dissociation, we can actually mix a lot of this one that you're seeing here. Right? So that's exactly what we are going to have. Then the next thing I'm going to talk about is actually what? Is actually the relationship between pKb and also what? Kb itself. Right? So pKb actually indicates what? The power of what? Of dissociation constant for what? Of base. Right? So whenever we have, let me simply say, increase in what? In Kb. Whenever there's increase in Kb, you see that there's going to be what? There's going to be let me simply say, there's going to be, the base is going to be what? A very strong base. It's going to be what? A strong base, since there's increase in what? In the pKb. Right? And whenever there's what? There is increase in pKb, in Kb, that's why there's going to what? Be decrease in what? In pKb. So that's what it means. So if there's decrease in what? In pKb, that's why there's increase in what? In Kb. So that's the relationship between them. So increase in what? In Kb, that's why there's that base is going to what? Is going to be strong. So as the Kb keep increasing, that's the more strong base that we are having. And don't forget that not all bases actually have what? Hydroxide agent in their structure. You have to take note of that. So it's very, very important. So that's what's about this video.